We're facing an urgent crisis, one which threatens our very existence, the climate catastrophe. The climate stability of the past 12,000 years has come to an end, and around the world we are now suffering from the impact.
Greetings to all viewers. My name is Mayur Gyanchandani, and the topic for my project is design and control strategy of a standalone PV fast charging station for EVs, and the supervisor for the project was Dr. Mohammad Nasiruddin. The project discusses the fact that there are rising carbon emissions across the world, with 2021 alone set to record the second highest rise in recorded data, with 20% rise over 2020 emissions. And a lot of this is also due to transportation. And in Dubai's case, it's almost one third of all carbon emissions across UAE. The project studies a off-grid solution to essentially reduce the load on the conventional AC grid and to provide a safer and a more efficient fast charging solution that's based on photovoltaic power and a battery backup storage. The charging controllers proposed in this project also ensure battery safety and faster charging speeds than current charging infrastructure present. Now, having a look at the results that were obtained for each of the fast charging methods, the first one we'll be looking at is constant current charging, where we can see that the voltage essentially goes into a state of overvoltage by going over 4.655 volts. That was actually the maximum rated voltage for this battery. This has been a concern that was shared in the literature review as well and in the project in the results analysis as well. The next charging the next charging method that we'll be looking at is CCCV, or the constant current constant voltage charging method. Over here, a key difference that we can see is that the current starts reducing linearly at the point it reaches around 1500 seconds, where you can see that once the voltage reaches the threshold set at 4.6559, the current starts reducing, but the SOC keeps rising as the battery is still being charged, but it's being charged at a reducing current. The last one is a multi-level charging. Over here, it's similar to what we obtained from constant voltage, as the voltage is held constant now, but the current is reduced in separate stages. So what happens in this case is, once you start reducing the current in separate stages, you essentially get a charging cycle that's relatively faster, but at the same time, it does not compromise on the battery health, as was the case with constant current charging operation. So the first mode of operation is where there is excess per PV power generation. Excess in the sense that it is more than the demand required for charging the connected electric vehicles. So in this case, what happens is, as we can follow the arrows shown, the photovoltaic system essentially provides and becomes the primary source of power. It essentially powers up and charges all the connected EV batteries and also charges the BESS with the remaining power. The second mode, however, discusses a case where there is inadequate power generation from the PV array. This could be due to a drop in irradiance, but what essentially means by this is that there is a drop in the PV power and it cannot match with the demand that is there for charging the connected EV batteries. In this case, the station is designed to essentially use the PV array and the BESS to sort of work in combination and share the load to charge for the charging demand. Essentially, what the BESS now does is that it compensates for the deficit in power. So the last mode is where there is no power generation from the PV array. This could be due to nighttime or fog, or in cases where there is a fluctuation in the PV array system itself. In this case, what happens is the BESS now becomes the sole power supply for the entire charging station and takes over the responsibility and takes over the load to provide for in terms of the charging demand from the connected EV batteries. The results that were obtained for each of the modes of operation. The first mode is where we expect the PV power to be at its peak and the BESS to not provide any power but instead charge, and the EV battery to essentially be in a state of charging. Here we have a small excerpt from the charging cycle that was shown earlier, but essentially it's there to prove that the charging is happening, that the battery is being charged. But we can see that there is no power obtained from the BESS, but there is peak power from the PV output, and the EV battery is still being charged. The next mode is where there is not enough PV power, but there is more of a charging demand from the connected EVs. In this case, what happens is once the PV output power drops, as we can see around the middle of the provided results, the BESS power immediately takes over and shares the load, essentially compensating for the deficit power. And this has been designed to be in a seamless and inefficient in an efficient way, sorry, that it does not affect the charging cycle in any way, thus helping keep the charging cycle steady and not providing any fluctuations in the charging cycle for the EV battery. The third mode was where there is no PV power generation, and in this case, as we can see towards the end of the first graph given for the PV power output, there is 0 watts being generated right now. And then once there's a state of 0 watts, we can see that the system switches to become the primary source of power. As you can see, the BESS now becomes the primary source of power. But again, the station and the entire system is designed to not have any impact on the charging cycle. That's why we can see that despite this switch, there's not a major fluctuation, there's not any major impact on the charging cycle. Conclusion: the proposed multi-level charging algorithm is a good trade-off between charging speed and battery health. The proposed charging station does work in line with the expected parameters and does match the expectations that was set for the charging station design. And the work done in this thesis can be pushed further into different fields and can potentially include AC grid generation, V2V charging, or even neural networking and controller design to obtain better and more accurate SOC levels and to have a more granular control in charging cycles.